Hi everyone. Today we're going to wrap up this week with a mini lecture on the greenhouse effect. Just like I said last week, at this point you should have already watched the YouTube playlist because in this video we're just going to tie up some loose ends. Alright, this week we've spent time learning about the greenhouse effect, which is the natural process that traps heat in the atmosphere and makes our planet livable. Without the greenhouse effect, the sun's energy would be absorbed by the Earth's surface and then quickly re-emitted and lost to space, leaving our average global temperature at negative 18 degrees Celsius. This would make Earth more like Mars and completely uninhabitable. Luckily, we still have our atmosphere and a greenhouse effect, so the solar radiation is absorbed, re-emitted from the Earth's surface, and captured by our atmosphere, allowing much of that heat to stay near the surface. And this is what gives us a global average temperature of 15 degrees Celsius, which is very pleasant compared to the other. Our atmosphere is unique in its having greenhouse gases, which include carbon dioxide, methane, nitrous oxide, water vapor, and many, many more, but these are the top four. And because they are greenhouse gases, they're clearly very important, but only make up a small portion of our atmosphere, which mostly consists of nitrogen and oxygen. The greenhouse gas with the greatest concentration is carbon dioxide at only 0.04%, a tiny fraction of the entire atmosphere, and yet incredibly powerful in terms of heat trapping capabilities. How do these infinitesimally small gases make such a big impact? Well, this is due to their absorption window. Each greenhouse gas, and generally all gases in the atmosphere, absorb radiation at specific wavelengths known as atmospheric windows. In these charts, we see the atmospheric windows for the total atmosphere and some greenhouse gases, with wavelengths plotted on the x-axis and absorption percentage on the y-axis. Also plotted here is the visible spectrum, which is what we are able to see, and consequently what gets through our atmosphere the best, since it isn't absorbed very much. Generally, the sun emits in shortwave radiation, which includes both UV and visible, and while the Earth emits long-wave radiation in the infrared spectrum. Although these labels down here, long wave should really start here, right above the red of visible. So kind of ignore these labels, and just remember shortwave is visible radiation and shorter, while long wave is greater than visible. Okay, so if we look at the top portion of the chart, we can see which windows are absorbed by these gases over the entire atmosphere, and there are multiple absorption peaks across the spectrum in both short and long wave radiation. Moving down to ozone, we can see there's a wide absorption window for UV radiation. Oh my gosh, sorry about that. Right there in UV radiation, as well as some narrow peaks in the long wave spectrum. Now, ozone is interesting because the majority of our atmosphere's ozone is actually in the stratosphere in what we call the ozone layer. And since it likes to absorb UV radiation, this highly concentrated region of ozone actually protects us from the sun's most damaging rays by absorbing it way above our Earth's atmosphere. Our Earth's surface. As you've probably heard, UV radiation is very harmful to our health and can cause skin cancer, which is why our sunscreens have UV blocking abilities and why we have had global initiatives to protect the ozone layer and shrink the ozone hole, which is something we'll talk about more later. Now, remember that ozone is a greenhouse gas. We know that means it captures heat. And its capturing of UV radiation in the stratosphere leads to increased temperatures in that layer, which is why, like I mentioned last week, the temperatures increase with height in the stratosphere instead of decreasing like in the troposphere. So all in all, the ozone layer is a good thing. Like the natural greenhouse effect, it benefits life on Earth, but ozone doesn't only exist in the stratosphere. Sometimes it's forced into the troposphere by strong storm systems, but more commonly it forms as the result of nitrous oxides and methane interacting with sunlight. And as we can see here, ozone also likes to absorb some long-wave radiation, which contributes to the enhanced greenhouse effect, albeit in very short timescales, like days to weeks. But this is why you'll sometimes hear people differentiate between tropospheric and stratospheric ozone. Sorry if you can hear my dog. Okay, moving on to the next three plots. We see the atmospheric windows for methane, nitrous oxide, and carbon dioxide, the greenhouse gases we are most familiar with. And these mostly exist in the troposphere. Looking at our graph here, they all absorb long-wave radiation, which is what makes them so effective, or make them effective greenhouse gases, since they really like to absorb the Earth's radiation. Our last gas on this chart is water vapor here at the bottom, which exists almost entirely in the troposphere. It has many absorption peaks in the long wave part of the spectrum, and this makes it a very effective or a very efficient greenhouse gas, contributing to about 50% of its warming effects. It's also one of the most important greenhouse gases because its atmospheric concentration can be upwards of 3%. This is quite a bit higher than the 0.04% of carbon dioxide. So why don't we place the same blame on water vapor as we do carbon dioxide? Well, there's a couple of reasons. For one, water vapor isn't a significant byproduct of burning fossil fuels. But more importantly, it's because water vapor can transform into liquid, unlike other greenhouse gases. This diagram of the water cycle shows all the different states of water and how it moves through Earth's systems, like evaporating off the oceans and condensing into clouds or into rain in the atmosphere, and then that will precipitate onto the land. Sometimes it falls as snow, and that'll melt back into other sources of water, which can infiltrate groundwater, and plants can uptake that water and also transport it through evapotranspiration back into the atmosphere. And since water is always moving and changing across the planet, atmospheric concentrations vary widely, and the amount of radiation absorbed by that water varies widely too. This doesn't mean water vapor isn't important. No, not at all. It still plays an important role as part of the enhanced greenhouse effect through a process called the water vapor feedback. So let's break this down. As the global air temperatures increase due to greater carbon dioxide concentrations, this actually leads to more water vapor in the atmosphere because warmer air has a greater capacity for water vapor. Now, that may seem a bit confusing. So I'm going to show you a graph, but I want to assure you, you don't need to memorize this graph. I just want you to understand the relationship represented here because it's crucial to understanding this feedback. This graph has mixing ratio plotted on the y-axis with temperature on the x-axis in Kelvin. So what is mixing ratio? Mixing ratio is a measurement we use to measure the amount of water vapor in the air. It's the mass of water vapor in grams over the mass of dry air in kilograms. And this blue plot line represents the amount of water vapor that's required to reach saturation at a specific temperature. So as we can see here, when the temperature increases, so does the amount of water vapor that's needed for the air to be saturated, meaning more water vapor can be evaporated into the air at higher temperatures. And this makes sense logically. Like in the wintertime, when the air is saturated and it's snowing, it still feels really dry, right? Like the amount of lotion that I have to use in the winter is bananas. But in the summertime, when the air isn't even close to being saturated, it feels really sticky, especially here in the Midwest. In Colorado, it always feels kind of dry. But the higher temperatures have a greater capacity for water vapor, making it feel less dry than in winter. Even when it's not saturated, the air just doesn't feel as dry. All right, back to the feedback here. So we've increased our temperature, and that leads to more water vapor in the atmosphere. But because the water vapor is also a greenhouse gas, this leads to temperatures increasing further, and the cycle just keeps going. This is known as a positive feedback loop because the original input, in this case increasing temperatures, is amplified. And this feedback loop is why we can't discount the effects of water vapor in global warming, because even though the greenhouse effect is natural and gives us the perfect conditions for life here on Earth, we have disrupted the cycle. By increasing the amount of greenhouse gases through burning fossil fuels, we've set in motion things like the water vapor feedback and created an imbalance in the planet's radiative forcing, which is the difference between the amount of solar radiation entering our atmosphere and the amount of planetary radiation leaving our atmosphere, ultimately pushing global temperatures higher than we want or need. Okay, folks, that's it for this week. I'll see you in the next video.